Hi, this is JbPralay. Now we will know birth of the solar system. Around 4.5 billion years ago, our sun and all the other objects that orbit around it were born from an enormous cloud of interstellar gas and dust, similar to the glowing emission nebulae we see scattered across today's night sky. Astronomers have understood this basic picture of the birth of the solar system for a long time. But the details of just how the process happened have only become clear much more recently, and now new theories, discoveries and computer models are showing that the story is still far from complete. Today, it seems that not only did the planets form in a far more sudden and dynamic way than previously suspected, but also that the young solar system was rather different from that we know now. The so-called nebular hypothesis - the idea that our solar system arose from a collapsing cloud of gas and dust, has a long history. As early as 1734, Swedish philosopher Emanuel Swedenborg suggested that the planets were born from clouds of material ejected by the sun. While in 1755 the German thinker Immanuel Kant suggested that both the sun and planets ferment alongside each other from a more extensive cloud collapsing under its own gravity. In 1796, French mathematician Pierre-Simon Laplace produced a more detailed version of Kant's theory, explaining how the solar system formed from an initially shapeless cloud. Collisions within the cloud caused it to flatten out into a spinning disk, while the concentration of mass towards the center caused it to spin faster, just as a pirouetting ice skater spins faster when they pull their arms inwards towards their bodies. In the broad strokes described above, Laplace's model is now known to be more or less correct, but he certainly got some details wrong, and left some crucial questions unanswered. Just how and why did the planets arise from the nebula? And why didn't the sun, concentrating more than 99% of the solar system's mass at the very center of the system, spin much faster than it does? Solutions to these problems would not come until the late 20th century, and some of them are still causing doubts even today. Much of what we know about the birth of our solar system comes from observing other star systems going through the same process today. Stars are born in and around huge glowing clouds of gas and dust, tens of light years across, called emission nebulae. Well-known examples include the Orion Nebula, and the Lagoon Nebula in Sagittarius. The nebulae glow in a similar way to a neon lamp, energized by radiation from the hottest, brightest and most massive stars within them, and remain active for perhaps a few million years, during which time they may give rise to hundreds of stars forming a loose star cluster. Since the brilliant, massive stars surge and die rapidly, it's only the more sedate, lower mass stars like our own sun that outlive both the nebula and the slow disintegration of star cluster. Star-birth nebulae develop from the vast amounts of normally unseen, dark gas and dust that forms the skeleton of our Milky Way galaxy, and subside as the fierce radiation from their most massive stars literally blows them apart. The initial collapse that kickstarts formation can be triggered in several ways, for instance by a shockwave from a nearby exploding supernova, or by tides raised during close encounters with other stars. However, the biggest waves of star birth are triggered when material orbiting in our galaxy's flattened outer disk drift through a spiral-shaped region of compression that extends from the galactic hub and gives rise to our galaxy's characteristic shape. Inside the nebula, stars are incubated in huge opaque pillars of gas and dust. As these pillars are eroded by outside radiation from massive stars that have already formed, they break apart into isolated dark globules whose internal gravity is strong enough to hold them together, the seeds of individual solar systems. Gas falling towards the very center of the globule becomes concentrated, growing hotter and denser until eventually conditions are right for nuclear fusion, the process that powers the stars, to begin. As star begins to generate energy of its own, its collapse stabilizes, leaving an unpredictable stellar newborn surrounded by a vast disk of gas and dust that will go on to form its solar system. But how? The first person to put Laplace's hypothesis on a sound theoretical footing was Soviet astronomer Viktor Safronov, whose work was first translated from Russian in 1972. Safronov's modified solar nebular disk model allowed the solar system to form from much less material, helping to resolve the problem of the Sun's slow star-birth nebulae develop from the vast amounts of unseen, dark gas and dust that forms our Milky Way. Spin. Also, Safronov provided a basic mechanism for building planets out of primordial dust grains, known as collisional accretion. This simple mechanism involves small particles colliding and sticking to each other only at a time, eventually growing into objects that were large enough to exert gravitational pull and drag in more material from their surroundings. This produced objects called planetesimals, the largest of which might have been about the size of the dwarf planet Pluto. A final series of collisions between these small worlds created rocky planets close to the Sun, and the cores of the giant planets further from the Sun. The difference between the two main types of planet is then explained by the existence of a SNL line in the early solar system, around the location of the present-day asteroid belt. Sunward off this, it was too warm for frozen water or other chemical ices to persist for long enough, on the rocky material with high melting points survived. Beyond the snow line, however, huge amounts of ice and gas persisted for long enough to be swept up by the giant planets. It all sounds simple enough, and has been widely accepted for the best part of 4 decades. But now that seems to be changing. There's been the beginning of a paradigm shift away from the two-body buildup that Safronov modeled, says Dr. Hal Levison of the Southwest Research Institute, SWRI, in Boulder, Colorado. The idea of things growing by collisions hasn't really changed, but over the last 5 years, new theories invoking the idea of pebbles are coming to the fore. We've only now got to the stage where we can discuss these ideas in any great detail. The new approach stems from a long-standing problem. The big question is how you get the first macroscopic objects in the solar system, things that are bigger than, say, your fist, explains Levison. Safronov's idea was that you just did that through collisions, but people have always recognized there's a problem we call the meter barrier. You only have to look under your bed to see plenty of evidence that when small things hit on another, they can stick together, making these dust bunny clumps that are held together by electrostatic forces, weak attraction between innate static electric charges. And if you look at objects bigger than, say, a few kilometers across, gravity can hold things together. But if you're looking at something, say, the size of a boulder, it's hard to imagine what makes them stick. Fortunately, 10 years ago, researchers including Andrew Uden and Anders Jansen came with a way around the problem. What they've shown is as dust grains settle into the central plane of the protoplanetary disk, that causes a kind of turbulence that concentrates the pebbles into large clumps. Thank you for watching. Please like, share and subscribe my channel.